Good morning to all of you. Hello. Am I audible?
Yes, sir.
Okay. Thank you. So today I would be take two lectures. One now, and after the completion of this lecture at the regular time 11:50 again I have the second lecture. Okay. So first of all we have to be continue from the previous section, that is we have taken yesterday FSK, binary FSK, transmission and detection or generation and detection. So yesterday we have seen the concept how to generate the FSK signals, or what is the structure of the FSK transmitter, as well as we have seen that how the FSK signal has been generated, what is the principle behind this, how the frequency has been varied according to the binary data. So where we have learned that for the binary 1 we have increased the frequency, carrier frequency, and for the binary 0 we have decreased the carrier frequency. As well as we have also seen the spectrum of the FSK and the bandwidth of the FSK that we have got, that is 4 times of the FB. That is actually the twice of the bandwidth of the BPSK. Because in the BPSK this is only 2 FB, but in the case of FSK it is a 4 FB. Now we have to be learn how to detect the FSK signals. So if you have to be find that about the everyone please note it down, this is a two different techniques that we have to be receive or detect the FSK signals. That is, one is the coherent BFSK receiver. So here you can see here ST is nothing but the BFSK signal that we have generated yesterday. So this is ST is BFSK signal that is pass through the channel, and some noise would be added, and then it would be received by the receiver section. So first of all, this FSK signal has been feed to the product modulator, where it would be multiplied with the orthogonal carrier signals. So here in this case we have to be locally generate the carrier signals. Okay, and that is the phi 1t and phi 2t is there. Generally phi 1t we are all familiar of this. What is this phi 1t? That is 2 upon ts cos 2 pi f h t. Okay, and phi 2t is what? It is square root of 2 upon ts sine 2 pi f l t. Okay, so this two carrier signal has been multiplied with the received VFSK signal, and further it would be passed through the integrator. Okay, so and then whatever the output of the integrator S1 T and S2 T, it would be feed to the adder, that would be add these two signals actually, and add and subtraction of the addition and subtraction has been performed on this particular mixer, and then whatever the signal would be generated, that is YT, and that would be passed through the decision device. According to the value of the Y, it would be put up a decision that the received signal is binary 1 or binary 0, and decision device having some threshold level as well. So what actually going on in this particular coherent binary FSK receiver, if you have to be see that, so there are the two correlators for the two frequencies of the FSK signals, because we know that in the FSK we have to be vary the frequency signals, okay, according to the binary symbols. So here there are two correlators we are going to use here in the receiver section, having for the two frequency of the FSK signals, and these correlators would be supplied with a locally generated carrier, that is phi 1t and phi 2t is there. And if the transmitter frequency is FH, then the output S1t would be generated. If the transmitted frequency is the FL, then the signal S2t would be generated. And generally, if you have to be see the output, S1t would be generally greater than that of the S2t. And finally, you have to be see the output of the mixer, where it would be merged S1t and S2t. and we have to be generate the output signal, that is yt. And this yt signal would be then fed to the some decision device where it would be having some threshold level, and if yt is greater than 0 of this threshold level, so it is, we see that it is a binary 1, and if it is less than 0, we say that it is a binary 0 has been detected. So in this way we have detect the actual data that we have transmitted through the VFSK transmitter. Okay, so this is very simple operation of this coherent BFSK that I have derived, and all of you please note it on this diagram. This is important to understood the concept how the BFSK signal would be generated. Okay, now that same that I have told you that it is mentioned in this particular slide. Now the another way of detect the or receive the detection of the FSK signal is a non-coherent detection. So in the coherent detection, the frequency of the carrier at the receiver end would be matched or synchronized with the frequency of the transmitter end. But in this case of the non-coherent, there is a the frequency of the carrier signal would be maybe not matched, so it has to be some other way that we have to be used here. For that purpose, if you have to be see this structure, so ST, that actually BFSK signal, that is ST, it is equal to square root of 2 ps cos omega naught t plus dt omega t. Omega is here change in the frequency or shift in the frequency shift actually. So this signal would be received by the receiver end, and then it is passed through the two filters. It is actually the uh, band pass filters are there, BPF band pass filters are there, and that band pass filter, the upper band pass filter is tuned at the frequency of FH, and lower one is tuned at the frequency FL. Okay, so the bandwidth of band pass filter is also mentioned that it is having B twice of FB is there, that is FH and FL is there. FH is F naught plus omega upon 2 pi, that is F naught plus FB, and then finally FL is F naught minus FB is there. And then when it is passed through the band pass filter, that the output of this band pass filter would be uh, the signal having the frequency component that is tuned to the FH and FL respectively, and then it would be passed through the envelope detector, and where the envelope detector would be discard the DC component if any present, and only pass the frequency component having the FH and FL frequencies, and then output of the envelope detector has been be fed to the comparator. Again in the comparator there is a comparison or the between these two signals would be there, and according to that finally the binary data DT would be detected. Okay, so this is the another way that you can also uh, receive or you can detect the BFSK signal by using the non-coherent way. Okay, so there is a two way that you can generate the uh, FSK signals, sorry, receive the or regenerate the binary data from the FSK signal. One is the coherent detection, another is a non-coherent detection. Okay, now if you have to be see there, uh, that is the same thing I have mentioned here. The signal is applied to band pass filter with the center frequency of FH and FL, and here we have assumed that FH minus FL is twice of FB, and then the filter frequency ranges do not ever overlap, and each filter having the pass band wide band enough to encompass the main lobe of the spectrum. Hence the one filter will be pass nearly all energy in the transmission at FH. Okay, so and finally the filter output are applied to the envelope detectors, and envelope detector output would be compared by the comparator. So basically what is a comparator? Comparator is a circuit, we know that that accept the two input signal, and if the binary it generate the binary output which is at the one level, and the other depending on which is the input is larger. So the comparison is there done there, whatever the signal is larger that would be considered as the output signal DT, and that would be decided as a binary 1 or binary 0. So this is the way that you can regenerate the data from the received VFSK signal. This is the structure of the VFSK receiver. After that, we know that after the generation and regeneration detection, we have to be little bit discuss about the signal space diagram of the signal. So here the signal space diagram of the VFSK signal has been discussed. So in this case, if you have to be see that unlike the BPSK, there are the two orthonormal basis functions are required that to represent the we can say to represent this particular phi 1t and phi 2t. Phi 1t is and phi 2t are the orthonormal signals actually. That would be a carrier signal actually, orthonormal carrier signals, that is having the amplitude of the square root of the cos 2 pi f1t, and phi 2 is the cos 2 pi f2t, where the t is in between of the 0 to bit period t p. Okay, so t here f1 is means what you can say, f1 is nothing but your fh. Okay, so here you can refer it is also f1 is nothing but the fh actually, and that is equal to if you have to see the fh is here m fb, and fl is equal to your n fd, that is the fundamental frequency of the carrier signal. Fb is there, so fl is the n times fb and fh is the m times fb is there. That's why it is represented with the another uh, notation, that is f1 and f2 is here. Okay, so if you have to be plot the signal space representation, so you would be found the s1t or sht, that is equal to square root of the eb phi 1t actually, and similarly to the s2t is the square root of eb phi 2t. And if you have to be plot the coordinate of this s1t, so it is square root of eb 0, means x coordinate is square root of eb and y coordinate is 0 actually. So s1 is basically lies in the in phase component, means x axis. Okay, and similarly at the y2, if you have to be s2, you have to decide it will lie on the y axis. That's why the x component is 0 here and y component is square root of eb. So that could be understood with of this particular diagram, that is actual signal space diagram of the BFSK signal. So here you can see that S1T, that is you can consider also the SH as well, and S2T is SL. So it is having the amplitude of square root of EB. I am representing it in terms of energy signal. You can also represent it as a power signal as well. So how the power signal would be represented, instead of this you can use the term P as PV. Both are same actually. The different way that you have to be represent only, and this is the actual positions of the carrier, orthonormal carriers, and the if you have to say the BFSK signals are there. So one is tuned at the FH frequency, another is tuned at the FL frequency, and the distance between of these 2 points in the signal space diagram, that would be considered as the Euclidean distance. So D is here Euclidean distance. So it is a very simple mathematics. Use the Pythagoras theorem, and use the square root of this square plus this square would be considered as a 2 times of square root of EV is there. So this is the equivalent distance between the two signals points of the SSK binary SSK signals on the signal space diagram. So this is all very important terms that you have to be always keep in mind, that like the bandwidth of the scheme, either it is a BPSK, BFSK, as well as the what is the amplitude of the Euclidean distance, how to represent the signal space diagram, that is also important. So here you can see that the two carrier signals are also normal to each other, because in the BFSK signal we have modify or we have modulate the frequency only, the phase and amplitude is kept constant. Okay, that's why it will be two different axes that is having the in orthonormal in nature to each other. Okay, so I hope all of you have drawn this till now. As after defining this particular equivalent distance, you can this is all about the binary FSK signaling. Okay, Now we have to be switch to a very important topic. We have learned the ASK, PSK, FSK. Now we have extend our thinking, and we have to be go for the some signaling technique where we have to be combine the bits. See, still whatever we have learned, that is only one bit information, means either binary 1 or binary 0. Now we have to be learn in the quadrature phase shift keying technique where we have to be going to make a symbol that is made up of the two or more than 2 bits. Okay. So in general, phase shift keying technique we that uses the phase shift of 90 degrees, that is we have already seen, or but four different signals generated. If you have to be going to generate the four different signals, so for that you have to be combined 2 bits. Okay, so means 0 0 0 1 1 0 1 1. In this way, if you have to be when you have to be going to combine these 2 bits, and so what is the advantage of this combining of the bits? It would be increase the data rate in the PSK. Okay. uh, and at the same time our bandwidth would be not affected. Bandwidth is same, but our data rate is increased because we have combined the two bits into one symbol. Similarly, you can use for the 4A, it is an example for PSK, you can use the 8 PSK, N PSK, that is called the A-Murray signaling actually, that we will be also learn after this QPSK as well. Okay, so that is the main idea behind this QPSK, that we are going to combine the symbol bits into one symbol, more than one bits. Before that, we have only learned the one bit at per symbol. This is some types of the QPSK. Generally, that is a conventional QPSK is shown here, and offset QPSK is also shown here. Then pi by 4 QPSK is shown here. But we have to be go through the basic. These are some constellation diagram actually. I and Q quadrants are in phase, and quadrature components are shown here. In the x-axis in phase, in the y-axis quadrature components are shown here. So we would be come to this, but start from some basics of the QPSK. So what is the basic principle that we have to be used in the QPSK signaling? So if you have to be see here the basic principle. So first of all, in the communication system, we know that generally there are the two main resources, that is transmission power and channel bandwidth. So in the communication system, there is a two main resources, that is a transmission power and channel bandwidth. That's why we have to be draw the power spectral density of all the signals. Okay, so the channel bandwidth depends upon the band pass transmission. Okay, channel bandwidth would be depends upon the band pass transmissions. Depends upon the bit rate and signaling rate actually. Sorry, the channel bandwidth would be depends upon the bit rate or signaling rate FB. And in generally digital band pass transmission, a carrier is used for the transmission. That's why this carrier is transmitted over the channel only. Okay, so in this case, if you have to be going to see, if two or more than 2 bits are combined in some symbols, then the signaling rate is reduced, and therefore the frequency of the carrier is also required less, and this reduces the transmission channel bandwidth also, or maybe bandwidth is same or maybe reduced. Okay, this is one of the benefit of combining the signals also in a one particular symbol. So thus, because of grouping of bits in the symbols, transmission channel bandwidth is either reduced or either the unaffected. Okay, this is the one of the very good benefit of the combining the bits into one symbols. Your data rate would be increased, but your bandwidth would be reduced. So in the quadrature phase shift keying technique, two successive bits, what we are actually doing in the QPSK, two successive bits in the data sequence are grouped together. Means before in the BPSK we are only using 0 and 1, but here we would use the combining the two bits, means 0 0. There are four combinations could be possible: 0 0 0 1 1 0 and 1 1. So this reduces the bit rate or signaling rate, and hence reduces the bandwidth. And in the BPSK, we know that generally in the BPSK, what happens when the symbol changes the level, the phase of the carrier is changed by the 180 degree. Since there are only two symbols in the BPSK, and the phase shift occurs in the two labels only. Okay, but in the QPSK, as two successive bits are combined, this combination of the bits form the four distinct symbols, and when the symbol change to the next symbol, these symbols are symbols and their phase also shifts. Okay, but not by the 180-degree. We would see how much the amount of phase shift would be there. So this is the one of the description has been shown the symbol and corresponding phase shift in the QPSK. So if you have to be see that here I have given the symbol actually represented as the SI. SI is there. So here I is given as the value 1, 2, 3, and 4. So for that there is a four combination as shown as S1, S2, S3, and S4. For S1 you have to be see here it is 1 0. There is a two successive bits has been combined, and phase shift in the carrier would be occurred as a 5 by 4 only. Okay, so 45-degree phase shift would be there. That is shown that how the 45-degree phase shift could be shown through the waveform. That is see here. We are very much familiar that how the sinusoidal signals would be represented basically. So it is a 0, it is pi by 2, it is pi by 4. Okay, it is pi, it is 3 pi by 2, then it is 2 pi. So it is basically if you have to be see that this is pi by 4, then here in between pi by 2 and pi there is a 3 pi by 4 somewhere 135-degree, then pi and 3 pi by 2 there is somewhere it is 5 pi by 4 actually, and in between of the 3 pi by 2 and 2 pi there is a 7 pi by 4 is 315 degrees actually. So these are different positions of the signals where we have to be different angles as will be shown. So why I have drawn this, so that you would understand that pi by 4 means it would be start in between here somewhere. 135-degree means it would be start somewhere here. So you can see here. 225-degree means it would be start somewhere here. That's why it is shown here. Okay. Similarly, the 315-degree would be shown somewhere here, and you can see also uh, how the signal will be propagate. So in the 45-degree, it would be increasing in the positive direction because there is a 90-degree somewhere. Then in the 135-degree, it would be moved toward the negative side because after 135, there is a 180 would be came. So it would be goes in this direction. Okay. Similarly, 225, it would be very much near to the 270-degree. Okay. So that's why it would be goes like this, near to the 270-degree. Okay, then 315-degree, after that there will be 360 would become like this. That's why it would move in this direction. So this is the way that we have to be represent this QPSK signals actually. Okay, so you have to be remember that how to plot when you have to be, because waveform is very much important when we have to be learning the any shift keying technique, either it's a BPSK, BFSK, ASK, or QPSK, or any other MRE, PSKs, FSKs are there. So we have taken the four combinations, maybe not sequential way, but there is a possible combinations are there 1 0 0 0 0 1 and 1 0 1 1, and corresponding phase shift has been shown here. Okay, so in this way you can say that what is the corresponding phase shift, like it is 1 0 maybe, and it is 135 means 0 0, it would be 225 means 0 1, and it is 1 1. Okay, so this is very important and basic representation of symbols that would be carried the further concepts of the QPSK. Okay, I hope all of you have drawn till this table as well. Okay, now come to the operation and waveforms of this particular technique. So as for the, there is some steps I have mentioned here. The first step is input sequence converted. As per the transmitter diagram, if you have to be refer this transmitter diagram, it will be show a diagram of the QPSK signals transmitter. The input binary sequence is first converted to the bipolar NRZ signals are there. Okay, and this signal is called the BT, and it represent the binary 1 by the +1 volt and binary 0 by the -1 volt. This is actually the OQPSK transmitter. It is not directly written as a QPSK, it is written as OQPSK, offset QPSK transmitter. Why it is called the offset QPSK, we would become later on the discussion. But first of all, you can see that the block diagram of this transmitter. Okay, please everyone noted down this diagram or take the screenshot of this. So first of all, we have to use a general binary data sequence in the terms of 1-0 form. Then it would be fit to the polar NRZ level encoder that would be convert this binary sequence into the polar signal, that is BT. So BT could be for binary 1 means it is a +1 volt, binary 0 means it is a -1 volt is there. And then this polar NRZ signal has been be given to the demultiplexer. So this demultiplexer will be split this polar NRZ signal into the two different parts. We know that every signal having the even component and odd component. So it is suppose odd, so second one is even, then odd, then even, like this. Okay. So 0, 1, 2. So it is 1, 2, 3, 4, like this. So even and odd components are always there. Okay. So in this way we have to be represent. So in this way it would be split this demultiplexer will be split this NRZ signal into the suitable even and odd components. So upper one is the BET, that is even component. Then lower one is the B not T, means odd components are there of this bipolar NRZ signals. And this even component is then fit to the product modulator, where it would be combined with the orthogonal signal, that square root of the PS, or maybe you can write it as a square root of 2 upon TS as well. Either of this cos 2 pi f naught t, there is a carrier signal, and odd signal would be with the sine 2 pi f naught t. So you can see that there is a phase difference between both of them. It is a cos, and 90-degree phase shift is the sine pi. Okay. So and then there is the SET, output of this even and carrier signal combination, and this odd and sinusoidal signal combination S naught T is there, and these two signals would be finally added to the fit to the adder, when it would be add these two signals, and finally the QPSK ST would be generated. Okay. So I hope all of you have drawn this diagram. If you still not, please take the screenshot of this, because that would be carry the further discussion. Okay. So if you have to be refer this diagram, so second step is input sequence converted into NRZ. Then second is demultiplexing in odd and even number of sequences. So this demultiplexer divides the BT into the two separate bit streams of even and odd. BT represent the even numbers, BO not represent the odd number of sequence. And this symbol duration of both of these odd and even number sequences is 2TB. Okay. So time period of the each bit, so twice of time period of each bit is there. Thus the each symbol contains 2 bits. Why is it 2TB? Why not TB? Because here we are combining the 2 bits, 0 0 0 1 1 0 1 1. That's why the bit duration would be also increased. Symbol duration is increased by the twice of TB. Okay. So after that, observe that the first even bits occurs after. Generally, we have to be know that how the signals has been represented digitally. So always we know that the even bit would be always come after the odd bit, that I have shown here. Suppose odd 1 2 3 4. So even number always come after the odd. So that's why also here the first even bit would be occur after the first odd bit. Therefore, even numbered bit sequence is BET starts with the delay of 1 period due to the first odd bit, because the even bit would be generated after odd bit. So there is some delay you can consider. Both bit would be not come simultaneously. So even would having the 1 bit period delay as compared to the odd bit. The first symbol of BET is delayed by the 1 bit period TB with respect to the first symbol of B naught T. That's why this delay of TB is called offset, and hence the scheme is called as the offset QPSK. Okay. Now you understood why it is called offset QPSK, because the even symbol is having the some delay of the bit period TB with compared to the odd symbol. That's why it is called the offset and it is called an offset QPSK. This shows that the changes in the level of the BET and B naught T cannot occur at the same time. Because of this, offset or staggering, also we can say the staggered QPSK. Okay, so this is the way that why it is called the offset QPSK. Now the third step is that after demultiplexing, splitting in the odd and even components, we have to be modulated with the help of the orthogonal carrier signals. So modulation of this quadrature carriers. Okay, so in this case, modulation of quadrature carriers, the bit stream BET modulates the carrier square root of PS cos 2 pi f naught t, and V naught t modulate the carrier square root of PS sin 2 pi f naught t. And in between of these two, why I am saying it is orthogonal signal, because both carrier signal having the 90 degrees phase shift in between of them. These modulators are balance modulators actually, and these carriers are also called the quadrature carriers. And the two, if you have to be see in the remember on through this diagram, it is also very much clear that what I am saying about. So this even and odd are, then in the product modulator it is, we have to be merged with the orthogonal carrier signals. Okay. So if you mathematically you can write ACT, now two modulated signal, even modulated signal and odd modulated signal, BET square root of the cos 2 pi f naught t, and then it is sin 2 pi f naught t for the odd signal. So in this way you have to be write these equations. Okay, so this is I hope this is the first equation actually, so you can give them as a number for your easiness of all these calculations as well. Equation number 1 and equation number 2. Okay, then after this modulation process, what we have to be do, this ACT and S naught T is what, these are basically BFSK signals, but it is BPSK signal actually, but we have to be combine these two symbols, odd and even component, to make it into the QPSK, because in the QPSK we are combining the two successive bits. So successive bits are odd and even bits. So that's why here we are going to combine these two even and odd component and make these two BPSK into the QPSK signals. So addition of the modulated, first step is addition of modulated carriers, and the adder of this figure would be added these two signals BET and B naught T, as given ST is equal to, this is a QPSK signal, ST is QPSK signal, that is summation of the ACT plus S naught T, that is equal to BET square root of PS cos 2 pi f naught T plus V naught T square root of PS sin 2 pi f naught T. This is your equation number 3. Okay, so this is your actual QPSK equations as per this structure. In some books, they have used the cosine signal with the odd component and sinusoidal signal, sine signal with the even component. That you can also do. That is also correct. It is also correct. Either of the concept you can refer. Okay. Now, after generation of this or modulation of these carriers, we have to be available the OQPSK signal. So you can see that what amount of phase shift is going on. So the step number 5 is the QPSK signal and phase shift. So in the QPSK signal that we have generated through this particular transmitter, if there is any phase change, it occurs at minimum duration of TB. After every TB, maybe there is a phase change. If there is any phase change, if there is no phase change, there is not any issue. But if there is any phase change, that would be occur at minimum duration of TB. For this duration, the phase change would be continued. And this is because of the two signals have ACT and S naught T have an offset of TB, because even an odd signal having the offset delay in between of that of the TB. Okay, and because of this, the phase shift is of the QPSK is actually the pi by 2. for every TB second. Phase shift would be a what? Pi by 2 for every TB second. Okay, so this is for the generation of the QPSK signal. You can see the phase shift by this phasor diagram as well. Simultaneously, you please start to fill up the attendance. And one announcement I want to give that at whatever the time is going on now, 11:30, 29. At 11:50 again the next lecture would be of the digital data communication would be there, where I would be complete this topic. Okay. So this is the phasor representation of phasor diagram for the QPSK signal that would be showing you that how the phase would be occur. There is the four symbols are there. See that it is not this is your in phase and this is your quadrature component. I and Q axis are actually there. So in the in phase there is a carrier frequency of square root of cos omega naught t, but you can see the quadrature component is here, not in the positive axis, it is in the negative axis. Okay, and negative or minus square root of ps sin omega naught t is shown here, minus square root of ps cos omega naught t is there. So basically this is the carrier signal, that is the red line I have underlined. Okay, and the symbols, this combined symbol would be not available at this axis, it would be in between of these two in phase and quadrature axis. Okay, that's why it is a quadrature phase shift keying. And this is the first symbol, you can refer it is as 1 0. So first is the 1 is even symbol, that is 1, and 0 is the odd symbol, that is -1. Then it is again 0 0, when both the symbols are in this axis are negative, -1 volt. Then it is you can say 0 1. So here MSB is the even and LSB is the odd, remember this. It is -1 and this is 1, and this last one is the 1 1. Okay, these are the 4 points where these four quadrature symbols are located on the signal space diagram. Okay, so always remember this. And this is the way that we have to be show the phasor diagram of this QPSK signals. Okay, and if you have to be moved from one symbol to the another symbol, you have to be follow the path that would be across this axis, okay, of 180° or maybe 90° maximum. Okay, maybe 90° path would be there generally. In the offset QPSK you have to follow 90°. In general QPSK you have to follow the 180°. Okay, so thank you all of you for attending this lecture. After this we would continue the receiving of the QPSK. Okay, so after this we would be go for the waveform of the QPSK as well as the reception of the QPSK signal. Thank you all of you. We join at 11:50.